Good afternoon, everyone. My name is Siddharth Ravikumar. I'm the product manager for Solido IP validation at Siemens EDA. Today, our topic of discussion is IP/QA best practices in the IP production and integration flows. So as the agenda for today, we are going to be starting by talking about the different IP/QA challenges in the semiconductor industry today and how we can go towards achieving a robust IP/QA. Then I'm going to touch upon a few example issues in the IP production and integration flows. I'm going to introduce you to Solido Crosscheck, the IP/QA framework, and how it basically helps with IP handover, best practices, as well as scaling within large organizations. So as you probably know already, design IPs play a crucial role in the design of modern SoCs, and they've increased in usage with the rapid evolution and complexity of modern designs. So design IPs, as you know, enable reuse, thereby reducing development time and cost. So given that IPs are used so much in the industry today, it is really crucial that they are validated both by the production as well as the integration teams, because undetected issues have the potential to cause silicon failures much later. So the qualification costs are almost up to $40 million today based on different tech nodes and types of IPs. So when we talk about IPs, they could be of several types, right? So they could be analog or digital IPs, standard cells, IOs, memory IPs, and so on. So each of these IPs are basically represented in different views and formats. They could be your front-end views, like your .lib, Verilog, VHDL, SDF, your back-end views, like your LEF, DEF, GDS, your simulation and schematic views, as well as other different views. So given that you have such a large number of views and formats, it's not only important that you validate these views and formats on their own, but also with respect to one another. And this is really important because your IP data basically comes from different stages of your design flows, and it's represented in different views and formats, as we discussed earlier. And finding inconsistencies later in the flow as we go through the design stages could cost you in terms of money and schedule cost, right? So this could range from hours to months. And as a direct impact of this, in addition to your obvious tape-out delays or suboptimal PPA performance, you could run into more serious issues like your pre-silicon ECOs, as well as silicon failure, or your chip could just come back and not work. So this is just to show you some of the inconsistencies across your different views: physical views, logical views, electrical views, and other views. So here we are kind of highlighting the inconsistency between LEF, Verilog, CCS, and open access. So these are some of the issues that we can catch. And I'm going to be talking more about the different kinds of examples that we can see in this flow. So based on what we've seen so far, a robust IP/QA is an essential step to silicon success. So what is the goal of such a robust IP/QA methodology? So one, we need to ensure that the design views are correct and consistent with each other. It should be agnostic to any tool set in the design flow, and it should be agnostic to the IP type or even the tech nodes. It should ensure that the IP performance is in line with the specification documents. So this results in IPs that are much easier to integrate, and they help reduce your production schedules. So now I'm going to talk about a few example IP issues and the challenges generally the industry faces today. So here's the first example issue. As discussed earlier, IP libraries often have large amounts of data. In the case of standard cells, we're talking about thousands of cells. In the case of analog or digital macros, this could be hundreds of pins. And then when we talk about Liberty files, we have to multiply them with the number of PVT corners, which could be a large amount. So we might run into terabytes of data. So here in this example, we are having LEF, Verilog, Layout, and Liberty, which are just 4 of the many formats that we can have. So certain issues like cell name mismatches or missing cells um, may incorrectly limit the cells taken into consideration by synthesis or place and route tools, resulting in some soft errors which might cause suboptimal PPA performance metrics. So pin name mismatches or missing pins are often caught by your downstream tools, but again, there's a lot of work in cleaning up your IP data before you actually go ahead with your flow. And some of the issues like macros or cell area mismatches that we can see here, as you can see, the left Liberty and GDS have a difference in the area. These could be more subtle and can be missed during library import. So if these kind of errors are uncaught, they can lead to inaccurate assumptions made by synthesis and place and route tools and an incorrectly optimized design overall. For larger IP blocks, this could be more catastrophic. And if you basically need to design, you'll need to make some changes in your plan to change that to remedy this particular issue. So another kind of issue that we see is the power domain mismatches between SPICE and CPF or UPF domain specification. So this particular issue applies to IP blocks such as your digital or analog macros, which are supplied along with their own UPF and CPF. So this includes differences between UPF and CPF specification and the actual SPICE netlist for a related power and ground pins of a given pin. So this kind of error often results in the wrong power domain information used. Simulations and timing analysis may assume that a portion of logic or netlist is inactive during the incorrect power domain shutdown cycle, for example. Now, you might be able to catch something like this in your layout versus schematic checks, but then again, you have to do substantial rework to remedy this. So the final example I'm going to show you is the timing arc inconsistency between Verilog and the Liberty models. So a large portion of data in the Liberty models or your .libs are based on your timing arcs, which has information about, which tells the static timing analysis tools the timing dependency between the different pins of an IP. So Verilog files also can do this with certain system tasks, so like your $setup hold. So a problem basically arises if the timing arcs are different between the Liberty and the Verilog. This leads to inconsistent timing results, incorrect timing analysis, and in general, unpredictable problems between synthesis, digital simulation, and sign-off, which are very difficult to root cause based on where your downstream tools are getting its timing arcs from. So that leads me to talk to you about what Solido crosscheck is and how Solido crosscheck is going to kind of remedy most of the challenges that we spoke about, the different kinds of IP issues that we spoke about so far, what Solido crosscheck basically does. So crosscheck basically is an IPQA framework which has about 300 plus IP validation checks that can be applied across different views and formats. And this is just not a scripted flow, but it also has a supporting framework like user-friendly reporting, visualizing, and debugging, and also the ability to add waivers to those errors that are not going to affect the quality of the IP. And we have something called the crosscheck QA exchange deck that helps in aligning the IP provider and IP integrator on what the IP QA goals are for a particular IP. And last but not the least, we have the ability to add custom functionality to what already exists natively within crosscheck by the extensibility with APIs. So you could add your custom checks, your custom formats, or even generate your custom reports using these APIs. So this is a broad classification of the different kinds of checks that we can do with crosscheck. And they are classified as cross-view consistency checks, where you want to ensure your database, your terminals, your pins, and your timing arcs are consistent across your database. Crosscheck also performs library and layout checks, such as checking for consistency of a cell. You want to make sure your cells are present across a library, and then functional equivalence for standard cells and other layout versus layout checks. For example, you want to make sure that your pin location or pin size differences between your left and your GDS. Some of the checks can be performed within a single format, such as the static, timing, power, and noise checks. And we have other miscellaneous checks like power domain checks and other custom checks that we can add using the cross-check API that I spoke to you earlier about. So what design views and formats can these checks be performed on? So these checks can be done in any of these supported designs as long as the check is supported or the format supports that particular check. We've already discussed at the breadth of the coverage. So you can see that it includes the front end views like your Verilog, VHDL, your backend views like your left, def, GDS. We are also supporting binary databases like Milky Way, Open Access, NDM, and other miscellaneous views. Again, just like how the checks were used, we can use custom formats by using the cross-check API as well. So in the next few slides, I'm going to be talking about the supporting framework around cross-check. All right, we did talk about what the checks do, what formats it supports. Now, what is the surrounding frameworks? Like I said, it's not a scripted flow. It has a supporting framework and the built-in reports. So I'll start with the reporting. The built-in reports basically are available in HTML and CSV, but you as a user can also generate your own custom reports based on your requirements using the APIs. The report shown here is an example of the HTML report. On the left side, you can see the rule numbers, the rule description, the duration of a particular check or a rule, and then the category in which they are put into, or the bucket, right? Either a pass, fail, or wave category. For each of these entries, we can get a more detailed view by actually probing into those errors. So you get a first level analysis of why a particular thing failed and what could be the reason for it. So crosscheck also provides a very good visualization context for different views and formats. So you would be able to open up the layout views or symbols or schematic or even waveforms for different cells. For example, if you wanted to bring up the a MUX2 cell for your open access as well as the left side by side and want to view them, you would be able to do it. Crosscheck also has some message analysis features that help you debug really quickly what are the inconsistencies across different formats. And then this is an example of a metal shape inconsistency between the left and the GDS. So this kind of visualization context or debugging context helps you complete your debugging much faster. So waving messages in crosscheck is pretty straightforward, and you could just do that by clicking on a particular error and then clicking on wave. So this is an example of the current waivers we've set, and they are saved into a waivers file. And whenever you add a new waiver, you can also add a reason for the waiver, which basically helps in accountability and tracking. And then we can click on the wave button. With this, every item is considered waived and will be marked appropriately in the report. So if any other user is basically bringing this up, they would be able to see why a particular waiver was there and who waived it and why, the reasoning behind it. One of the key visualization features allowing users to manage their validation results is the bottleneck analysis tool. On the first run, generally any QA tool might show you a number of violations. So in order to ensure that you're not spending too much time on high impact errors, you need a graphical representation of different statuses. And that's what the bottleneck analysis provides you. And this, sorry, this is extremely helpful because it reduces the number of violations um, very quickly. And then by just looking at a few of these high impact violations or fixing a few of these high impact violations, we can bring down the number of violations to a large extent. So that is basically the benefit of using the bottleneck analysis tool. So I'm going to be talking about the handover best practices. In the industry, you need to have an alignment between your IP provider and the IP integrator. So this next few slides are going to be talking about that. So the IP integrators basically need a way to communicate their IP quality goals with the IP vendor with information such as the IP completeness, which basically checks whether the IP data has all the relevant information. And then we also talk about IP integrity to check what are the inconsistencies between the different views and formats within that particular IP data. And then IP integration to check the IP compatibility with the different EDA tools that are used within the flow. So for that, CrossCheck has something called the QA Exchange deck. I did touch upon this when I gave you the overview of CrossCheck, but here's a little more detail on that. So CrossCheck QA Exchange deck basically helps facilitate the alignment between the IP quality goals between the IP integrator and the IP supplier. So essentially, it is providing a powerful handshaking system between the IP production and IP integration teams. I'm going to give you a little more detail on what goes on in this QA Exchange deck flow. So the QA Exchange deck is basically created automatically using Solido crosscheck after the IP integrator and provider align on what the IP quality goals are. And then the IP provider uses this QA Exchange deck and ensures that errors are detected much earlier in the flow. It is used as a sign off for the IP release. And then once that sign off is done, it is shipped to the IP integrator. Now, both the IP provider and integrator can choose to classify some of these results as waivers based on whether those waivers are actually going to affect the quality of the IP. And then lastly, the IP integrator. Let's say the IP integrator chooses to enhance the QA on the IP. The QA exchange deck can be updated and then sent back to the provider. And then we can repeat the same process once again. So now that we've spoken about the challenges and how CrossCheck can help with those challenges with its features, we're going to be talking about what else can CrossCheck do and how can it help in terms of scaling across large organizations. So an organization can basically deal with multiple IP types, process nodes, PDKs. Moreover, team sizes can grow, multiple IP teams can exist within an organization. So to reduce the engineering time, IPQA framework should be seamlessly deployable across different IPs and teams. So a robust IPQA flow therefore requires extensibility via APIs that suit the needs of your organization to add custom functionality in addition to what natively exists. So in that respect, one of the key strengths of CrossCheck is that it has a full set of APIs that help you add additional custom functionality that doesn't exist natively in the tool. For example, let's say you want to programmatically set up cross-check based on changing input parameters, you would be able to do that using something called the setup API. And what if you wanted to use your own custom checks or custom formats? You can do that by using something that we call the cross-check API. And let's say you have a downstream flow that wants to use a specific or wants to use some specific information from cross-check. Well, this can be achieved by using something that we call the DB API, which allows you to query the database and provide information that you require. So this is one of the more popular use cases amongst our customers where they can create a QA setup that works with a larger environment. And all these are pretty easy to set up because they are based on the version 3 of Python. So in summary, so let's just recap on what we basically spoke about, right? We spoke about why IPQA is really important by talking about what the challenges are and giving you a few examples of what occurred. And then we introduced you to Solido Crosscheck, which is an IP, a complete IP validation framework, and it is tool flow agnostic. It includes about 300 plus checks today, and it's not just a scripted flow. It includes reporting, waving, and visualization. The extensibility, which allows the user to add custom functionality to what already exists. And then we finished off by talking about the IP handover and the best practices between the IP supplier and the IP integrator. So overall, you need a robust QA system to improve your production cycles and also improve the quality of your silicon. And Crosscheck helps you do that. So with that, I think I'm done with my presentation. I will not be there to answer your questions. Julian, who is in the webinar, will be answering your questions. Thank you for your time.